Hi, I'm Mike Miller. I'm a software developer and enterprise architect. And over the last 5 years, I've been working on a software project on my own time. It's my hobby to build a mind or build a brain for a little robot that I have to control the robot. So today I'm going to talk about artificial intelligence, the science and the impact for our presentation, BIT, Los Angeles. So we're going to go over a little bit of terminology. We're going to talk about some of the people in the industry. And then we're going to talk about knowledge, since knowledge is at the root of most everything that has to do with artificial intelligence. We're going to talk about knowledge representation, knowledge creation, knowledge manipulation. Then we're going to talk about architectures for controlling devices like this robot or like your smartphone. And then we're going to talk about the impacts of artificial intelligence technology and automation in general. And we're going to talk about the threats and opportunities. So to begin with some terminology, intelligence. There's many definitions of intelligence. Ask everyone. They have their own. For the purposes of this talk today, we're going to say that intelligence is the capacity for thought, creativity, and problem solving. And the definition of intelligence is usually a receding definition, because when we make new discoveries, whatever we discover is no longer intelligence. Intelligence is something else, or it's something other than, what it was before the discovery was made. Artificial intelligence is generally attributed to John McCarthy. He made that statement. He coined that term around 1955, 1956, and it's simply intelligence as exhibited by machines. And they made two distinctions: weak AI and strong AI. Weak AI is small, different little programs that may seem smart, but they're not equivalent to human intelligence. And then strong AI, which is human level intelligence. And some examples are Deep Blue, which is a chess playing program; Watson, which is a Jeopardy question answering program; Cleverbot, which you can find on the internet, which is a chatbot you can chat with; Siri, which is a personal assistant; various expert systems. Then there's machine learning techniques and so on. And artificial intelligence is also a receding definition, because once it works and people understand it, it's no longer AI. For example, Mathematica, at one time when it first came out, it was artificial intelligence. Now people understand it as just a program. And then also, successful systems in artificial intelligence, really successful systems, are not discussed because they pose a strategic advantage to the firms that build them, so you don't really hear about those. Some more terminology: artificial general intelligence. It's generally attributed to Shane Legg in 2002, who coined the term for a book by the same name. It's basically human level intelligence in machines, and what we consider a strong AI. Some examples from the movies would be Ava in the new movie Ex Machina, Chappie by the eponymous movie, Kit, Sonny from iRobot, the Terminator from all the Schwarzenegger films, and so forth. So that's artificial general intelligence. And then there's also artificial superintelligence, and that's superhuman level intelligence in machines. You might see that as HAL, which controls a spaceship in the movie 2001, Skynet in the Terminator series of movies, maybe Jarvis or Ultron or any of these other examples of superintelligence. When we talk about artificial intelligence, we typically tend to make the distinction between embodied and disembodied system. An embodied system is a machine with a body that interacts with the physical world. So, for example, a robot would be an embodied artificial intelligence system. A disembodied system is a machine that does not interact with the physical world. So Siri or Watson may be examples of disembodied systems. So learning is basically, in our definition, is improving your performance over time via inference and memorization. So you infer new things and you remember them. And that's generally how you improve over time. We have a couple kinds of learning. There's supervised learning, which generally is inferring a function from labeled training data. We'll get into that a little bit later, but basically you have some training data and you want to understand the training data, so you infer some kind of function that describes the training data. And unsupervised learning, which is finding hidden structure in unlabeled data. So in supervised learning, you tell what the categories are and you give instances to the learner. In unsupervised learner, you just give it raw data and let it figure out what the categories are. And typically, these are in artificial intelligence systems, not AGI or ASI systems, the supervised versus unsupervised. In general, unsupervised learning would be in the AGI and ASI. Although you could train it a little bit too, but generally you would just have the general intelligence just learn things from observing from all its sensors. A few milestones. 1956, there was a Dartmouth summer research project on AI, and that kind of kicked off the first people to discuss and explore AI. In 1997, Deep Blue beat Gary Kasparov. So that was a turning point. That a computer program could be the world's best chess player. In 2011, Deep QA, or Watson, beat Ken Jennings and Brad Rutter, who were the reigning champions of Jeopardy. So that was also another milestone, and it beat them handily at that. In 2013, the European Union's Human Brain project kicked off, and their goal is to model a full human brain by the year 2020. So a few trends in artificial intelligence. Back in the 1970s, there was natural language processing, which was mostly symbolic approach, which focused on microworlds or limited domains. In the 1980s, we saw rule-based expert systems arise, and that was also largely symbolic approach, although there were some statistical approaches as well. And then in the 1990s, they experienced what we call an AI winter, largely because of the success of the rule-based expert systems in the 80s. People didn't want to discuss or talk about or fund the successes. And so there was a dearth of, there was still a lot of activity in universities, but a dearth of commercial AI going on. In the 2010s, this era, now we're merging with machine learning and algorithms that learn from raw data. And just recently, 2011, 2012, deep learning, or using these deep convolutional neural networks, has become a trend as well. There are a lot of people working on artificial intelligence. These are just a few. I picked these because they have significance to me, but there are a lot of people out there working on this, on them. I guess the two most notable would be Isaac Asimov on this page, and he wrote about artificial intelligence more than worked on it, and Alan Turing, who came up with the Turing test. So Alan Turing developed the Turing test, and basically it's a test where a human evaluator judges a conversation between a human and a machine to decide which one is the human. The human evaluator can't see either the human or the machine. They just have to go based on this conversation, figure out who they think is the human. And Eugene Goostman, in last year, 2014, which was a chatbot program, It won a competition at the University of Reading by convincing 33% of the judges that it was human. The winner was required to persuade at least 30% of the judges. And the developers of that system were Vladimir Veselov, Eugene Demchenko, Sergei Ulasin. So they were the developers. Isaac Asimov is important because he devised what we call the 3 laws of robotics, which although fictional, served as a guideline to how robots should interact with people. Basically, a robot must not injure a human being through inaction or cause harm to a human being, cause a human being to come to harm. A robot must obey the orders given it by human beings, except where the orders would conflict with the first law. And a robot must protect its own existence as long as the protection does not conflict with the first or second laws. So, knowledge representation. So, in artificial intelligence, if you don't take anything else away from tonight, know that knowledge representation is the problem in artificial intelligence. It's the only problem, really. How do we represent knowledge? There are 3 kinds of approaches to knowledge representation. There's symbolic approaches, what we call sub-symbolic approaches, and statistical approaches. Symbolic approaches are embodied by programming languages, such as OPS, which is a production system or rule language. It's called the official production system. Lisp, which is a somewhat esoteric programming language these days, but it was the main core programming language back in the 60s, 70s, 80s, and some of the 90s. Prolog, which is programmed logic, it's another programming language, and a language that I've developed actually, called Premise. I am another gentleman that invented a new programming language. Symbolic representations deal with ontologies, or taxonomies, which are graphical representations of which are node-link networks of how things exist in the world. So maybe at the top of the hierarchy in an ontology you have thing, and then you may break it down to natural and artificial things, and then you may break it down by phylum to maybe living things, and just an arrangement or organization. And the largest ontology so far to date was in a program called Psych. It has millions of these nodes, ontology nodes, and it's been handcrafted over the last 30 years. Graphs, which are node link diagrams which contain knowledge. The nodes are knowledge and the links are relationships among the nodes. Google itself has what they call a knowledge graph with entities and relationships among those entities. And then you have rules which allow you to operate on such ontologies or bases of facts and so on. An example representation, example symbolic representation is given below, where you have an idea that all people are mortal, all artists are people, all artists are mortal. So this is how you would represent knowledge in a sample programming language. This is in the premise language, this is how we do it. We have sub-symbolic knowledge representations, and these are typically neural nets, neural networks. So in a neural network you have a bunch of nodes, and you have connections between those nodes, which are called input nodes and output nodes. And they're largely fixed connections, and you input information into the input nodes, and you get information out of the output nodes. And basically, the links between the nodes are adjusted, the weights are adjusted. It's typically a fixed learning algorithm that relates the inputs to the outputs. And in deep convolutional neural networks, you have different levels. In recurrent neural networks, you have sometimes backward propagation where the information flows forward and backward. You also have image schemas, which are a sub-symbolic knowledge representation. They're not exactly symbolic, a little bit below symbolic. And these are recurring structures within our cognitive processes, which establish patterns of understanding. So image schemas are formed from bodily interactions, from linguistic experience and so forth, but they kind of represent concepts that are deeply embedded in our brains. So concepts like into and containing and out of. On a metaphorical level, these are concepts that are underlying most of our thought, because everything is a metaphor of that. George Lakoff has a book called Women, Fire, and Dangerous Things, and it's a really good book to learn a little bit more about. Finally, we have statistical knowledge representations, and these are often mathematical models. We have Markov decision processes where you model, you create a fixed model, but the weights in the model change. So you have a set of possible world states defined by variables. You have possible actions you can take. The action effects for each state affect the variables. And so when you take an action, that changes the value of the variables. And you have a reward function, so that when you take an action, you're either punished or reinforced for taking that action. Bayesian networks, they represent a set of random variables and their conditional dependencies via a directed acyclic graph. You can find a little bit more information on Wikipedia. And factor graphs, which is a graphical network representation for belief propagation. We can talk about knowledge creation. So those were knowledge representations. Knowledge creation is basically reasoning. You know, it's how we make new knowledge, how we infer things. And in reasoning, we look at what we call premises, which are just basically assumptions or statements about the world. We look at background knowledge, what you already know. So the premises represent a new situation, and the background knowledge is what you already know, what you already bring to bear, and then conclusions, the things that you can infer about this situation. So a gentleman named Richard Mikowski, he came up with what he called the fundamental equation for inference. And with that, he could do a lot of very sophisticated kinds of inference. But this is the basic equation, which is basically premises, or the current situation, along with background knowledge, entail conclusions. So the U, we can just call it with, and the line equals, we can call that entail, or proves, or derives. So in knowledge creation, so we have, let's take an example. Premise would be like, I think. Some background knowledge, maybe something that you already know, is I think, therefore I am. And your conclusion will be, I am. I am human. All humans are mortal. I am mortal. Right? So our premise is I am human. Our background knowledge that we already have stored up is that all humans are mortal. So we can conclude that I am mortal. So inferences can be either strong or weak. Strong inferences are always true, but they're what we call conclusive. I think, therefore I am, always I am. That follows. That follows conclusively. Weak inferences may be true. They're what we call contingent. They might be plausible, they might be partial, only telling half the story, or they might be probabilistic. If we say I am, and we know in the back of our minds, I think, therefore I am, I am, and the reason is maybe I think, or maybe something else, maybe some other reason for me being. Knowledge creation. deduction. So we can derive conclusions using this premises with background knowledge gives us conclusions. We can induce, or we can have inductions. We can hypothesize premises. We can say, take our conclusion with our background knowledge and hypothesize a premise. And then we can do analogy. We can hypothesize some conclusion. Give an example of this. So an example is, we say Jane's truck is a fire truck. And we know in our back of our minds all fire trucks are red. So we know always Jane's fire truck will be red. So this is deduction. And here we have the implication. We have the word implies. And in deduction, we're taking our premise and matching it up against our antecedent. This part of the implication is called the antecedent. This part is called the consequent. So in deduction, we match our premise with our antecedent of some rule in our background knowledge, and we come up with a conclusion. We come up with a conclusion. So the premise matches the antecedent. And in deduction, it preserves truth. I'm going to skip this next example because I don't want to confuse us. But induction is the opposite. Induction takes our conclusion, matches it with the consequent, and comes up with the premise. So if we say Jane's truck is not red, and we know in the back of our minds all fire trucks are red, then we can say always Jane's truck is not a fire truck. And induction is falsity preserving. The conclusion is false, the premise will be false. Right, it'll match. So we can take another example, a positive example, and maybe this will shed a little bit more light. We say Jane's truck is red, and we know all fire trucks are red, so maybe Jane's truck is a fire truck. It may not be, though. You know, it may just be red. It may be a red dump truck. So this is a little bit analogy. So in analogy, we hypothesize conclusions. We say Martha is similar to Betty, and we know that Betty is an intrepid woman. And we say if two things are similar, then they may have similar properties. We can conclude that Martha is intrepid. Knowledge manipulation entails three basic things: constructing knowledge, clustering knowledge, or classifying knowledge. In constructing knowledge, we build solutions, we build plans. In clustering knowledge, we create new categories from observations from data. And in classifying, we pick an option from among several options. So those are the three things we do in AI. So in knowledge manipulation, construction, you construct plans, you do constraint satisfaction. You know, if constraint satisfaction problem is a problem where it's like a jigsaw puzzle, you have to put it together. The man with the dog lives in the blue house. The man with the woman with the cat lives in the red house. The person who also likes cats is in the greenhouse. You know, which person owns which pet? You know, that's a kind of a constraint satisfaction problem. Still improving. You give it a set of premises, and you have to come up with some conclusions. Reasoning, which we already discussed. So this construction tasks, building chains of inference or actions. Clustering is basically grouping similar objects. You're given a bunch of data or a bunch of information or a bunch of objects, and you have to cluster them. How are you going to cluster them? They give you a bunch of toys. You have blocks, you have balls. You can cluster them round things and cubic things. Or you can cluster them by color. All the red things, be they blocks or balls, and all the yellow things, be they blocks or balls. You know, so clustering is just grouping things together. And you can actually install some category formation. Suppose you don't know what you have a yellow ball and a blue triangle. You put those two things together in a group because they don't quite fit. Well, that's another group. You have to name it. You can call it yellow ball, blue triangle. That's the new group. That's the new category. You form a new category. So category formation also. Classifying things. Basically, you're given a set of options, and you have to select one. And you can do that in a number of ways, through case-based reasoning, fuzzy logic, neural networks, Markov decision process. And the big thing these days is neural networks for playing video games. And the way they do that is they stream a lot of information from the video game, and they choose an action in the video game. So are they going to move left? Are they going to move right? Are they going to fire their missile? Right? So they have maybe 3 actions, and you're picking from all this information which action to choose. So you're classifying the input into a choice, and you're executing that choice. That's how they get the neural nets to play video games. Case-based reasoning was big in help desk. Person calls in, they have a problem, my printer is not working, and you have to say, okay, what is this problem? From all the things that can go wrong with a printer, how do I find the one thing that is this particular person's case? So you ask them questions. You say, okay, is it plugged in? Is it turned on? Does it have streaks? Is there ink in the printer? And so on. And all these questions are actually attributes of the problem, or features of the problem. And so you're getting to that one particular problem out of all the possible problems there could be, and the solution associated with that problem. Architectures. There are a lot of different architectures for doing a lot of different things. I'm looking at architectures for controlling this robot. This is a Now robot. It needs a brain. It doesn't have a brain. So we're trying to build a brain. So how are we going to build a brain? And that's what we want to figure out, how to build a mind for this robot. There are a couple ways to build minds. You can build an individual mind. We say this square is a mind, and this circle is the robot that's in the world, or any kind of device, or a smartphone, or any device. Maybe your home with all the sensors in it, the thermostat, the alarm, and so on. The device is situated in the world. You have the mind. Maybe you have one mind that controls one device. Maybe you have one mind that controls several devices. At your home, it could be the garage door, the front door, the washing machine. You could, if you're driving a car or flying an airplane, you can have several minds controlling that one device. Because if one goes out, you don't want to be out of luck. You want to have some redundancy built in. And then you can have a hive mind, where you have a master mind, and you have copies of that mind that each control the device. So in this situation, I'm only looking at one mind, one body, or one mind, one device. So how are we going to build this thing? Right? We want to build a mind for this robot. So we need to say, in our mind, here's the body in the world, but in our mind, we need an area to perceive, to get sensory information. We need an area to be reminded. We need an area that has some kind of control, some kind of planning, and some kind of acting. And we have a basic loop we call a reaction loop. So from the body, we get sensory information. We get what we call exteroceptive information, external information from the world through our senses. We get interoceptive, internal information within our body that comes in. And then we also have proprioceptive information from our actions, what we're doing at this particular time. All that information comes in to some perceiving agent. Perceiving creates a situation, senses some solution selector or action selector, which picks a reflex or a habit and sends it off to be executed and done. So this is a basic pattern called a reaction pattern. If we want to think about what motivates this robot, well, the robot is motivated by power, a need for power. It's also maybe motivated by a need for Wi-Fi, for signal strength. So it wants to stay in range of the Wi-Fi transmitter, and it wants to make sure that it has ample supply of power. So these power and signal strength we call needs, and needs are expressed as urges. So they're called homeostatic variables, which means they have a target and they have an actual value. So target value may be 100%. We want power and signal strength to be at 100% all the time or close to it, but the actual value may vary over time. You know, as we wander around further from the modem, signal strength will go down, so we have to learn to correct and go back. As we wander around, power will go down, and we want to get it, you know, we have to know when to recharge. So these urges come from the body, and they get sent to an attention module, and the urges form goals, or intentions, what I call intentions. And so as the situation comes in, solution selector looks at these intentions. Oh, I need power. Oh, I need signal strength. And it picks some solution that's relevant to the intention, and it starts acting on it. So this is a motivation, basic motivation. And our attention module will reprioritize the intentions based on the strength of the urges. So as the urge deviates from the target value, the urge becomes stronger. It's the delta between the target and the actual value. Our solutions have to come from somewhere. So initially, we have some solvers working in the back of our minds, which subconsciously come up with ideas for you to try out. So this reflects the fact that when we get a situation in and we have a goal and we may or may not know how to solve it, some solver will produce an answer for us. You know, it's subconscious, but usually we say, hey, maybe I should try that. Or, hey, maybe I should try this. Sometimes we daydream. Daydreaming is basically perceiving the current situation and thinking about what you're going to do, and then creating a forward situation, and then cycling that through, thinking about what will I do next. And so your dream is constantly stepping through, but not actually taking the action, but you're stepping through. Compensation is basically learning. It's when you have a solution, you try it out, and then you wait to see if it worked or not, and if it worked, you reinforce that solution. You know, I was hungry, I wanted to watch TV, my solution was get some food, so I got some popcorn. So I ate the popcorn. That felt good, so I said, okay, next time I'll eat popcorn again. So you reinforce that. Basically, you can also correct the situation. You say, maybe I'll try a particular restaurant, and you didn't like the food, you didn't like the service, you say, well, next time I'm not going to do that. I'm not going to use that solution. I'm not going to go to that restaurant. So you regulate and you compensate for that. Solutions. And then you cope. Coping, basically, when you're struggling with a problem, you evaluate it and you say, am I making progress or not making progress? If you're not making progress, you have a couple choices. You can abandon what you're doing, you can postpone what you're doing, you can put more resources on it. So coping is basically how, or you can, you know, with people tend to talk about their problems or seek help, maybe cry for help, ask other people to help. So that's basically an architecture for coping. So I actually found all those patterns that you see by surveying a number of systems, and I put them all together in a system that I'm building called piagetmodeler, called the PANP2 system. And so when you put all those diagrams together, you get something that kind of looks like this. And basically, you have a body that's in the world, you have some observation components, some inferencing components, some learning components, and then some components for consolidation, meaning for forgetting stuff that's useless or old, or putting together and improving things that are useful. So impacts. So when will artificial intelligence take off to the point that we need to be scared about it? When will artificial intelligence really impact society? A lot of experts will give you different dates. The truth is nobody really knows. The truth also is that it will happen gradually and then suddenly, as everything happens, you know, generally. Things happen gradually and then suddenly. It's typically a long time to market for some AI products. Self-driving cars, the research began in the 1980s. We still don't quite have it yet. It's 2015. Google is testing some cars out, so are some other companies. Research in the late 1970s gave us expert systems in the 1980s, so it takes time for these things to come to market. Threats. So automation is more of a threat than artificial intelligence. Artificial intelligence is just one component in an overall march towards automation. So China has a government program called Replacing Humans with Robots.
That's the name of it?
That's the name of the program, Replacing Humans with Robots. They had a one-child policy for a long time that cut the birth rate in half between 1987 and 2003. Right now, they have a lot of students in university, 25.5 million undergraduates, and the students don't really want to do factory work. They're going to college and then they're looking for white-collar jobs, or they're going overseas. Outsourcing is happening now in China. They're actually outsourcing their low-wage jobs to places like Bangladesh. Xinbei, China, is replacing half of its 2.4 million workforce under this program. Some new jobs are tedious and backbreaking for factory workers. And they're giving grants and land subsidies to firms to go robotic. It's actually, because of the scarcity of factory workers, the government is helping assist this automation. And Medea Robotics is one company. It's cut its employees by half since 2011. Today, 20 years ago you had parking attendants at shopping malls. Today you have pay gates, so you stick in your credit card. The U.S. Postal Service workers used to do mail sorting, now it's automated. Video store clerks, if you can find a video store. Now you have Netflix and Amazon Prime. Tomorrow it might be doctors. Watson might replace doctors, we don't. Automation contributes to income inequality. Prior to now, the major changes in income distribution have been among workers, like CEOs getting more money than janitors, CEOs increasing their pay. So the emphasis was on a skill bias, the skills of CEO versus skills of janitors. There was actually a reversal in the year 2000, where skills were in less demand and still in constant supply, so the price of skills started to go down. In particular, we argue that about the year 2000, the demand for skills, or more specifically for cognitive tasks often associated with high educational skills, underwent a reversal. Many researchers have documented a strong, ongoing increase in demand for skills in the decades leading up to 2000, but they document a decline in the years since 2000, even as the supply of higher education workers continues to grow. So they show that in response to this demand reversal, high-skilled workers have moved down the occupational ladder and have begun to perform jobs traditionally performed by lower-skilled workers. This de-skilling process, in turn, results in high-skilled workers pushing low-skilled workers even further down the occupational ladder, and to some degree out of the labor force altogether. And they show this in a couple of graphs. As far as management, professional, and technical jobs, as well as in college graduates, the demand for skill. In the future, the prime cause of income inequality will be capital versus labor, not necessarily labor fighting amongst itself. So capital-based technological change is shifting the distribution of income from workers to owners of capital, and that has already started. Owners of income are getting a larger portion of income, whereas in the 40s and 50s, workers' income was high, owners was low. Nowadays, that's shifted dramatically. Some of the threats of better education won't necessarily reduce inequality if rewards go to those with the most assets. Economic crashes may occur since robots can produce goods and services, but they will not likely consume them. I mean, you'll have all these robots in the factory, but who's going to buy things if there's no money? And effects could be mitigated by basic income. If the government decides, or the governments worldwide decide to give people basic income, then that could probably mitigate some of these effects. But there's a political will required. I think Switzerland was the only country talking about doing a basic income for its. I don't know if they've enacted that, but I know that they've had discussions about basic income for its citizens. Some other threats: unemployment. Some indicators of unemployment, as they call the horsemen of the robotic apocalypse, are a decline in the total number of employed people, fewer job openings, middle class incomes flatten and race to the bottom as more people compete for fewer jobs. Corporations stockpile cash and invest less in new products and factories because they fear weaker sales. We've seen that already with the recession, the Great Recession that we had. But as we come out of this recession, we should, pay particular attention to these indicators. Some consequences of unemployment. Automation will eliminate middle-skill jobs first, according to Drum. The routine jobs that require no manual dexterity, accounting, customer support, and so forth. We've had civil unrest in the past due to automation. So mass economic displacements have not usually been peaceful. In the 1810s, we had the Luddites, and they revolted against the power loom by burning down mills and factories and destroying equipment. In the 1920s, there were the fascists. In the 1930s, there were the Nazis. In the 1970s, there's a lot of unrest in Detroit, a lot of strikes and protests. And then in the 2010s, we've had a recent example of Greece. Civil unrest in the 1970s is an interesting example. Between 1973 and 1980, with the city polarized, the 1973 mayoral election pitted black Democrat Coleman Young against Police Commissioner John Nichols. Coleman Young won. Expressing the outlook of Detroit's capitalist establishment, department store magnate Joseph Hudson remarked, "The black man has the feeling that he is about to take power in the city, but he is going to be left with an empty bag." After winning the election, Young oversaw the devastation of Detroit. Some 200,000 auto workers lost their jobs as the Big Three moved their operations out of the area. In 1974 to 1975, Young laid off city workers by the thousands. Services were slashed, school funding was cut, and the streets were flooded with cops. He opposed a proposed ordinance to disband the Detroit Red Squad, and he busted a city workers' strike to make the Motor City safe for the 1980 Republican Party convention. All this was carried out without any major protest. With mass unemployment also comes mass incarceration. Between 1973 and 1978, this was a period of substantial growth. During this 5-year period in the mid-1970s, Michigan's prison population grew from 7,874 to 14,944 prisoners. This is an annual growth rate of 13.7%. This is the second fastest growth rate in the 34-year study period. This wave of prison population growth followed 3 years of prison population decline from 1970 to 1973. So before this election, the prison population was actually on the decline. And after the election, and after all those layoffs, the prison population increased. The influx of prisoners in these years required the department to hire an additional 2,300 employees. The combination of prison population and workforce growth caused corrections spending to grow at an average annual rate of 26.6%, from 38 million in fiscal year 73 to 125 million in fiscal year 78. In a simplified model, two factors contribute to prison population size: the number of prisoners entering prison and the length of time the prisoners remain incarcerated. In this time period, both increased. So we can see on this chart, the years between 73 and 77, there was substantial growth in the prison population. And this coincided with mass unemployment in Detroit. And actually, if we look at this graph as well, we can see the years 1985 to 1989 also had substantial growth. And that actually, I think, coincided with the savings and loan crisis and the recession that began before the early 90s. So I think, there might be some positive correlation between high unemployment and incarceration. Just, looking at it cursorily. We can see there are threats that exist in warfare. Drones, or UAVs as they're called, and killer robots. I think last year in 2014 there was an article saying that the U.S. Army would like to obtain 1 million killer robots or 1 million soldier robots. When you have drones and killer robots, Asimov's 3 laws can't apply, because the drones and killer robots' main purpose is to kill people and destroy property. When you delegate kill decisions to drones and killer robots, the accountability is indeterminable for collateral damage. I mean, who is responsible? Is it the person that gives the order that allows the drones and robots to do their job, or is it the drone and robot itself? There's less risk to soldiers by using drones and killer robots, and that implies that it's easier to make the decision to go to war or to intervene in some area of the world. And since there is an international robotic arms race, that just necessitates that they be upgraded to ASI as soon as possible. It's commonly thought that the country with artificial superintelligence will have a strategic military advantage. That's just the current thinking. There are threats from hacking. Financial hacking. Target, the company, and as well as banks have been hacked. It could be hacking in telemedicine. Military systems hacking, that's definitely a threat, especially if anybody ever hacks, the nuclear launch codes or something like that. Utilities hacking, there's a lot of potential trouble there. And then there's a threat for artificial superintelligence itself. So what happens if ASI decides to use people for its own purposes? And they could manipulate people by giving them information that they want them to act on. Many different ways, but that's a threat to consider. But in the grand scheme of things, artificial superintelligence is probably not the most important thing to worry about, at least not today. We have climate change, we have nuclear war, we have ecological disasters to consider. You have, chemical pollution like the BP oil Gulf spill, or fracking earthquakes and waste. When you turn on your faucet and you can light it on fire, I think that's a pretty important threat to your existence. We have biological disasters. We pandemics like Ebola and biological pollution. Is an interesting thing here. Back in the 1890s and 1900s, early 1900s, or early 20th century, if you asked somebody what chemical pollution was, they couldn't tell you. They just scratched their head. Chemical pollution, what's that? But if you talk to somebody about 1979, 1980, 1990, and ask them what chemical pollution is, they could point to a number of examples. They could say, oh, okay, there's acid rain, there's oil spills, there's power plant wastewater runoff, many different kinds of, there's landfills, many different kinds of problems that are chemical in nature. Now, if you talk to somebody, this is the year 2015, if you talk to somebody about biological pollution and ask them what that is, they might scratch their heads. There's also threats from nanotechnology. The current thinking is that if nanotechnology gets out of the lab, it can run amok and turn the whole planet into gray goo. That's not a happy thing. We also have nuclear accidents like Fukushima, and we are still dealing with the effects of Fukushima today, several years out. And we don't know what the total impact of that will be or has been. We might actually also be invaded by extraterrestrial aliens. So that's also important to keep on the list of threats to human existence. And then militarized artificial superintelligence. That is a potential threat, but in the grand scheme of things, it's today it's not as likely or as important as the others. Automation. So that, besides the threats, there are a lot of opportunities. Automation actually is, there are opportunities in automation. If you actually can automate some jobs like customer service or accounting, there are companies that are willing to pay for those solutions. We know that jobs requiring manual dexterity are hard today. Robots aren't to that sophistication just yet. We know also that AI plus robotics might accelerate the pace of automation. And finally, with automation, there's some leverage to be gained, because today it takes fewer people to generate $1 billion than it did maybe 20 or 30 years ago. 20 or 30 years ago, a company to make $1 billion required thousands of employees. Today, there are companies with less than 20 employees that are billion-dollar companies. So, on the plus side, there are different opportunities out there, and we can leverage automation to our benefit. There are opportunities in healthcare. The U.S., under the Obama administration, the National Institute of Health has started the BRAIN initiative. It's brain research through advancing innovative neurotechnologies. The EU has put in €1 billion into the Human Brain Project, which their goal is to build a functional computer model of the human brain. There's convergences with big data today for continuous health monitoring. Watson is being fed medical information to assist doctors. There are opportunities to break into the field of artificial intelligence, through software development. You can learn to program different various languages: Python, Premise, Scheme, Prolog. A good resource for that is Artificial Intelligence: A Modern Approach. That will give you a lot of techniques that are used. It's a good introduction to the field in artificial intelligence. You can learn some software as a service APIs, like Watson's API, if that's available, and that will help leapfrog you into the programming aspect. Also, there's opportunities to learn data science. That will give you a good statistical background for some of the machine learning that's ongoing today and that's trending today. In sales, there are opportunities to join robotics companies or companies that are doing automation or companies that are doing artificial intelligence. And in hardware development, one can always just join a robotics meetup and socialize and find out how to build robots, what the software is that is being used, and maybe network for job opportunities as well. There are a lot of profitable application areas. Personal digital assistants, that's the biggest area. So like Siri, for example, someone said that had they not sold out, they would be sold out to Apple. They actually would have been on par with Google in another 5 or 10 years, because that area of personal digital assistance is a tremendous. It's just a nascent or incipient industry. There are opportunities in information retrieval and summarization, investing in trading, machine translation, video games, personal robotics, home robotics, environmental sensing and response, robot space exploration, intelligent tutoring systems. Just a number of areas, probably. And that's pretty much all I have for today. References are listed. There's a demo of Siri available online. And, if you have any questions, let me know. Send me an email, piagetmodeler@gmail.com. And you can take a look at my profile on academia.edu, on independentacademia.edu, Piaget Modeler. Thank you very much for your time, and thanks for listening.